This project involved creating a system that would use a piston that would go up and down to store gravitational potential energy. So what we planned to do was use a canister, put in hot water that would cause the air inside the piston chamber to expand and move the piston up. And then we put in the cold water, which would cause the air to contract and compress, and so the piston would move down. And thus we could use some sort of ratchet system that would store the energy that was created by moving the rack up, and then lock it in place when it moved down. During our testing, before we even created any ideas, we found out that if we put a 150-gram mass on top of the piston and did 5 minutes worth of cycles from hot to cold water, that would create about 2.947 joules worth of energy per cycle. That is calculated by W equals mgh, using h as 10 centimeters per cycle, and the mass is 150, and g is 9.81. This 10 centimeter height increase would cause the gear to rotate, and it was unclear at that time which type of gear we'd use, but we knew we'd have some sort of gear and a rack interface, and the rack would move the gear counterclockwise, and that would in turn wind up the string that was connected to our mass that was dangling below. And depending on the ratio between the gear and the winding wheel, the mass would increase by a certain amount. And the original plans, that was 1.33 radians worth of rotation, and would result in a 7.33 centimeter increase in height of the mass. Of course, this doesn't take into account the assumptions that we use, like ideal gas system, or that the gas would heat up first and then expand, not at the same time. And so this created about a 5% efficiency in the overall process, and that explains why our mass did not increase by 7 centimeters per cycle or anything like that. It was closer to a couple of centimeters, 1 or 2 maximum, and a total increase of 10 centimeters over 14 full cycles.
Our original design had a rack that was going to press fit into a circle and rest on the top of the piston, and that rack was going to interface with a gear, a large outer gear, and then inside that outer gear there was an inner gear, and it was going to ratchet on the teeth inside the outer gear so that it would spin when when the rack was moving in one direction but not in the other direction. And then we were going to have a little circle with, like, on the dowel with the gear that the string could wrap around so that the weight would lift and then stay up. Our original design had a few flaws. The first flaw was that we cut everything out of MDF because it's more flexible and would harder to break, and also it's less dense than acrylic, so we thought it would be better, but we didn't account for the fact that it has a much higher coefficient of friction than acrylic does. So that, and the fact that we had really tiny teeth and the laser curve was a little off, made it really hard for us to interface the ratchet gear as well as the rack and the gear. We went through so many gears and it really wasn't possible. When we did our calculations for our original design, we were calculating with an 150 gram mass, and we estimated that it would be about 8 to 10 full cycles, so the full 10 centimeters, and it was about 0.1 joules per cycle.
Because of all these issues, we came up with a new design. Our new design involved much larger teeth, so the interface was easier, and we had a rack and just one gear with teeth that matched the rack, and they were both angled. And then there was a little lever on the bottom left that we had a rubber band to keep the tension in. And so the rubber band would hold it up, and when the rack was moving down, the rubber band would prevent the gear from turning, and then when the rack was moving up, since it was a ratchet, it could click around and we could store potential energy by spinning the same. We filled the circle that the string could spin around and store potential energy.
Another thing we had to stabilize the overall structure was a heavy MDF press fit box that we used as a base and had the back plate slide into the top of it, so that we could put weights in the bottom of the box, and so the back plate couldn't move at all. We also had fasteners that stabilized around the piston itself, and that prevented the rack from shifting from side to side. It only moved vertically. And we had arms that went from the rack and clamped around the gear, so it would stay in line regardless of whichever movement it had to do. And we also made a slot in the rack that a string could be tied to, as you can see in our video. That prevented the rack from moving side to side as well, but it still gave it a little bit of leeway when I was moving down to slide over the gears.
You'll see on the arms that we have that hold the rack and the gear in place and in line with each other. There are holes because originally we were going to screw them in with fasteners, but the fasteners, when it was actually moving, were rotating, so they were like unscrewing themselves and falling off. And also when we used the hot glue, there was like extra space between the arms and the gear, so there was no friction there.
After conducting a moment analysis about the center of the wheel and the gear, we found that the mass itself that was pulling on the string required a 5 Newton force on the edge of the rack and the gear to actually cause the gear to move using the static equations.
The mass that we were using was 83 grams. Our hot water started at a temperature of 96 degrees Celsius, and our cold water started at a temperature of 4 degrees Celsius, and then our ending temperatures were 80 degrees Celsius and still 4 degrees Celsius. Our mass was raised 10 centimeters, so using mg delta H with a G value of 9.81 meters per second squared, we got 0.0804 joules of energy.
Some changes we could have made to the actual design was actually add more teeth, since we had 18 teeth on the entire gear. And towards the end of our testing, the piston was only moving up a couple of millimeters. And if we had more teeth, that would actually still click the lever on. But in these cases, we were getting no increase in potential energy stored. And that really affected our overall score pretty badly. We could have also increased the size of the wheel that the string wrapped around, because the ratio between that and the actual gear that was turning was quite low. It was quite a big difference. And had we increased that size, then each degree moved by the outer gear would have had more of an increase in the height gained by the mass. So that would be something we can look into for if we had to do it again.
We also could have used 1/8 inch acrylic because it would be a lot lighter than the 1/4 inch. We were using 1/4 inch because we thought it would be easier to interface the rack and the gears, but since we still had our arms, it would have worked with the 8 inch as well. And we also could have had a larger mass that we were lifting so that our change in potential energy would have been a lot higher. Especially because in testing, when we increased the mass, it didn't have it in fact went higher. It didn't affect the performance. And we also, on the same note, should have had a lot more testing and a lot more trials and tried different things. Another problem we had was that the rubber band, the tension was a little too much, so it was a little bit hard for the gear to make that the full rotation and to click. So with this design, we could have used a slightly looser rubber band. We tried a couple of rubber bands and we did try to loosen it. It's just hard to make it precise. And then we also could have redesigned the whole thing and had the lever above the gear so that the gravity would just pull it down and it would want to rest down, which would stop the gear from spinning in the wrong direction. But then when it was spinning in the correct direction, it would be easily able to push it up and out of the way so it would still spin.